If your revision relies on picturing a solid as a frozen, rigid grid of atoms, you are already losing marks before the timer even starts. Forget everything you thought you knew about static, unmoving solids, because that rigid crystal myth is likely costing you crucial grade boundaries in your Cambridge 9702 physics exam. Are crystals perfectly rigid, motionless structures? The short answer is an absolute no. Believing they are will completely sabotage your exam answers. We're shattering that myth right now.
You see, ordinary revision fails because just memorizing a static structure cannot explain why heat capacity changes with temperature or why some materials conduct heat better than others. The rigid crystal myth completely fails to explain macroscopic thermal properties. You absolutely need a dynamic picture to unlock those higher-tier marks and truly understand what is actually happening inside the material.
Section 1. The Physics Foundation. Vibrating atoms and phonons.
The crucial point here is understanding the fundamental difference between one isolated atom vibrating all by itself and a vast system of atoms vibrating together as a coupled network. This is what we call a lattice vibration. It's the collective, coupled oscillation of atoms about their equilibrium positions within a crystal lattice. They're not acting alone. They're a team working together.
Now, what's really interesting is how phonons give us the formal language to explain exactly how thermal energy is carried through a solid. A phonon is essentially a quantized unit of lattice vibration. Think of it as the ultimate bridge between classical vibration ideas and those complex quantum descriptions. It's literally the carrier of the thermal message.
And that brings us to the micro to macro chain. This is your first quick win. Whenever you're stuck in an exam, organize your explanation around this exact mechanism and its resulting consequence. First, atoms oscillate about their equilibrium. Then these vibrations couple across the lattice. Next, energy is carried via phonons. And finally, macroscopic heat capacity emerges. It's a perfect, unbreakable cause and effect sequence.
In a moment, I'll reveal the exact examiner clue that transforms a standard 1-mark answer into a flawless 3-mark answer. If you miss this, you're leaving easy points on the table. But first, you need the underlying framework that makes that specific clue incredibly obvious.
Section 2. The examiner's framework, transforming concept into marks.
This framework brilliantly illustrates how a structured, disciplined progression of ideas will usually score significantly higher than just an unplanned list of memorized facts. Here's the high-mark strategy. Step 1. State the concept. Step 2. Provide the evidence or data. Step 3. Apply scientific reasoning. And Step 4. Finish with precise examiner wording.
Let's take a mental checkpoint right now. Pause and predict. How would you explain the thermal properties of solids using this 4-step framework? Seriously, think about how you would draft this response in your head before we look at a very painful, real-world learner mistake that examiners see every single year.
Section 3. Spot the error. Flawed versus top-band answers.
Let's apply our framework to a Cambridge-style example and analyze exactly where students bleed marks. A flawed student answer might state a material has high thermal conductivity. Or maybe they simply name-drop a concept like phonons, but it fails completely to connect that measurable property to carrier motion or bonding. The core mistake here is confusing labels with actual explanations. Just saying phonons do it gets you absolutely zero credit if you don't explain the underlying mechanism.
On the flip side, the top-band answer models how to turn a short fact into a full explanatory sentence. It defines the concept of coupled lattice vibrations clearly and specifically connects the flow of phonons to thermal properties using matched language. It meticulously links the microscopic cause directly to the macroscopic effect. That's how you get the marks.
Okay, here's the examiner clue I promised you earlier. Essential missing constraints. Many learners completely forget to mention these specific constraints, things like temperature changes, material purity, structural order, or external field strength. These are so often the hidden requirements on the mark scheme that turn an average response into a top-tier answer. Always, always mention the conditions. Section 4. Escalating stakes. Real-world applications. The stakes rise in longer questions because a realistic application often provides the final, tie-breaking mark that pushes your grade up. For example, thermal management in modern electronics heavily depends on vibrational energy moving through solids. You've got to prove to the examiner that you understand why lattice dynamics matters far beyond the textbook page. It's about the real-world survival of complex electronic components. Concluding an extended explanation with one of these concrete examples demonstrates total mastery of the topic.
We are talking about spacecraft coping with extreme thermal shifts, high-precision temperature sensors, electronic power devices, or the acoustic design in engineered crystals. These real-life solid-state scenarios are your secret weapon for claiming those final evaluation marks.
Section 5. Final Exam Checkpoint. The Rapid Recall Summary.
Here is a 60-second recall protocol for you. Step 1. State the defining idea. Step 2. Name one mechanism. Step 3. State one measurable property. Step 4. Apply it to one real device. If you cannot confidently move through these 4 steps in under a minute, you absolutely need another cycle of active recall. It's just that vital to your success.
And when it comes to evaluating physics claims, always use matched language for comparisons. The golden evaluation rule is to include exactly one benefit and one limitation before reaching a conclusion. Whenever the command word asks you to evaluate or compare, this rigid structural rule will relentlessly protect your grade boundaries.
To truly master this topic, you have to fully internalize the transition from an isolated atom model to a collective network. That shift in perspective is the underlying foundation for every single high-mark strategy we've covered today.
So, we have successfully replaced the rigid crystal myth with a high-mark system, but how do you map this across the rest of the 9702 syllabus? Leaving this unsolved means your revision remains dangerously fractured right before the exams. You have the lattice dynamics strategy, but you need the whole interconnected picture to truly guarantee your success.
To excel in your Cambridge examinations, you must look beyond the textbook. As you continue your revision with our YouTube channel, Ace the Exams, I'll leave you with this final, vital question to think about. Why does collective motion matter more than an isolated atom model in a crystal? Master that answer, and you master the exam. See you next time.